Welcome back. So now here I am just further stressing upon, because you may have a question, what exactly 3 dB is? Why exactly 3 dB is? Remember, a circular polarized response is obtained when all these conditions are met. But to get these conditions over a wide band of frequencies, or maybe over 10 megahertz band of frequencies, it is difficult to achieve. Because see, Ex can differ from Ey. Phi x minus phi y mod of that may be equal to pi by 2 or maybe 85 degree or something. So all these conditions may not be matched at the same point. So for that, if any deviation occurs, it is basically an elliptical polarized radiation what you get. But it is not elliptical polarized where co and cross polarization level are within certain range. If it is 10 dB difference, if it is 8 dB difference, then definitely it is not a CP. But getting co and cross exactly equal in across all the frequencies, you need to have these conditions met. But we accept that okay, till say 3 dB difference point with respect to the co-polarization radiation, I will call that as a CP. Because whenever that happens, one condition or two conditions which are not met is Ex may not be equal to Ey or phase difference is not equal to pi by 2 radians. Because see, whenever we do an axial ratio measurement in the lab, ideally speaking, you should be measuring the amplitude difference as well as the phase difference of the orthogonal waves which you are receiving, right? And that's why we generally define terms called as LHCP radiation or RHCP radiation. Okay, these two components are obtained for the circular polarized radiation. In fact, these two components you can see it in simulation software also. Some of the simulation software do give this LHCP radiation and RHCP radiation. Okay, so a circular polarized measurement in ideal case should be done with respect to Ex and Ey, where the amplitudes are met as well as the phase difference has to be judged. There are set of equations which are using which you measure the power level in two orthogonal planes over a band of frequencies, and there are certain equations. Using those equations you can find out these LHCP and RHCP wave, and then you can plot them. Okay, so what will happen if you are plotting Ex and Ey or the E theta E phi plane, then what you will observe that co and cross polar level will be nearly equal. But when you are observing calculated RHCP and LHCP component, then the radiation pattern will be like this. Here the difference, this can be the RHCP excitation wave and this will be LHCP excitation wave. Which one is more dominant, that decides sense of rotation, whether it is a right hand circular polarized or left hand circular polarized. Okay, I am purposely not getting into that discussion right now because we will discuss it in detail later. Okay, so these two components, because see Ex and Ey, the field components will observe to be nearly the same. But from that, when you calculate these right hand and left hand circular polarized components, the difference will be like this. Because in linear polarized antenna, the difference between the RHCP and LHCP is nearly 0. Okay, whereas in circular polarized antenna, these two difference will be more than 10 to 15 dB. Whereas in Ex and Ey will be nearly equal. Okay, so this is about with respect to the measurements, how we do. Axial ratio is defined with respect to these conditions which are deviated away from the ideal case. Because it is very difficult, again I am saying it is very difficult to realize, because if you just design a circular polarized antenna, just to give you an example, just to give you an idea, you will see the axial ratio plot minimum at certain point. Okay, this is with respect to the antenna design. And then if you try to plot the Ex and Ey component, what you will observe that the Ex and Ey component, you may see the two components showing equal amplitude slightly away from the phase conditions. Whereas you may see the phase difference plot maybe showing a 90 degree at certain different. So effectively, considering all the parameters together, you will observe that conditions for circular polarization, because see here in this range Ex and Ey may not be equal, but Exy and Ey, the ratio may be 1 point or less than that. Phase difference may be 85 degree or 80 degree. So together these conditions are realized, and then you will get minimum axial ratio bandwidth. Again, that minimum axial ratio value will not be equal to 0 dB. It may be 2 dB or so. Okay, but that is the point of minimum axial ratio where these conditions of Cp together are realized. Okay, it is very difficult to realize everything at a one shot. Again I am telling you, it is together, all these effects together have to be considered. You can generate these field orthogonal field plots and their phase component using simulation software. CST does gives that. So, and then try to plot and correlate where is the axial ratio point is coming and where the difference in the phase as well as amplitude ratio plot is coming equal to unity. Okay, so all these put together gives me a limit that okay, Cp may not be the case that axial ratio or Ex by Ey is equal to 1 all the time. Phase difference should be pi by 2, but certain deviations from that is accepted, and then we define Cp bandwidth is the range of frequencies for which axial ratio is less than 3 dB. Okay, so this is with respect to the rectangular patch using a dual feed as well as a single feed where a microstrip line circuit was considered. We did talk about various field components, the conditions to realize Cp, then axial ratio, why axial ratio is considered. We did talk about polarization plots or the field plots as well as right hand and left hand circular polarization plots. Okay, one more thing I just want to tell here before going to the next section. Please remember this equal radiation, okay, or large difference between the RHCP and LHCP will be observed in certain direction. Okay, it may be seen that in the end-fire direction or maybe beyond certain angle, the difference between the field plots will be more, orthogonal field plots, or RHCP and LHCP components might be nearing equal in beyond certain angle. What this means is you do not have a circular polarized radiation beyond certain angular beamwidth. Okay, there are special techniques which are available in the literature through which you can realize wide beam CP antenna. Okay, of course the gain will reduce in those cases, but there are certain techniques through which you can realize a wide beam CP antenna. So what is the advantage of this? Rather, if you just place your antenna like this, your CP is realized in this direction. But if you have a wide beam CP, even in this direction, co-polarization and cross-polarization or RHCP and LHCP are meeting the requirement for CP radiation. So in this direction also, away from the broadside, what we call it as, or maybe in the end-fire direction, you will realize a CP radiation. So from practical application, yes, I require this kind of antenna, because I will just put my antenna like this, it is realizing equal power from this direction as well as this direction. So that is what is expected in practical case where any power, any direction signal can be picked up. Otherwise, here with respect to this direction, you are going to get a CP response. Okay, so here we talked about your single feed design, dual feed design, various parameters which are related to the CP response, the field components, the RHCP, LHCP, as well as I did talk about the phase plots. This in fact you should, when you simulate a circular polarized antenna, do look about this field polarization plot, that is Ex by Ey and phi x minus phi y. That is Just a second. Do look out for Ex by Ey plot and phi x minus phi y plot. In fact, these two plots should give you how and where a CP response is obtained with respect to minimum AR point. Okay, so now after this we will start with the slot cut designs to realize circular polarized radiation. So now I will start with a simple patch using a slot to realize a circular polarized radiation. What I am doing is I have taken a rectangular patch. Of course, similar designs we will talk about later in circular patch as well as equilateral triangular patch. And this is one of the best technique because we are not using dual feed, we are not using power divider, using a single patch with slight modifications in the patch, geometry using a slot and a single feed we realize a CP antenna. Now how it goes? Yeah, first of all, to realize a CP radiation, you should excite orthogonal modes. Now what I have taken is a square patch antenna. Okay, so when you have a square patch, that is L is equal to W, PM10, PM01 both are equal. Okay, you can have a nearly square patch also where L by W may be within 1 to 1.1. Okay, you can have a nearly square patch also. I am just explaining that with respect to a square patch, the same explanation is valid for nearly square patch also. Now, next step, to excite orthogonal modes, I cannot put a feed point either along the two axes which I have shown. Why? Because it will only excite 01 or 10 mode. I want both. So what I will do, I will put a offset feed location. So that offset feed location will excite 10, 01 as well as next higher order modes like 11. Okay, 11 we are not bothered about right now. Our focus is on realizing CP with respect to 01 and 10. Okay, now next step is what? If you just observe the resonance plot for this, if you just observe the resonance plot for this, you will see, I am talking about real curve, you will see a single peak. Okay, why? Because L and W are equal, 01 and 10 mode frequencies are nearly the same. Whereas in case of rectangular patch where L and W may be following this relation, you may see a two closely spaced resonant modes. Okay, so you have excited two resonant modes in this or a single resonant mode in this. Now what I want to do to realize a CP antenna, I should be having optimum spacing between these two mode frequencies. That optimum spacing will ensure that Ex is equal to Ey over a certain range of frequencies, plus it will ensure difference of these two within pi by 2 radians. So I should be having, this is very important point over here, optimum separation between the orthogonal modes. That will ensure these conditions which assist CP radiation. Let me tell you, I am using this word assist. Okay, because all put together gives me CP radiation. So these are the conditions which assist the CP radiation. So this I should be having. So closely spaced, optimum spacing is what? Interspacing between these two modes, or I should be degenerating 10 and 01. Degenerating means what? Separating. Now to do that, what I generally do, I can have a slot. I will have a slot cut inside the patch like this. Okay, I will have a slot which is cut inside the patch like this. What it will do? See, for 01 currents, slot is in parallel direction to the 01 currents. 01 currents are like this. For 1-0 mode current, the slot is orthogonal to the slot layer surface currents. Because of that, 1-0 mode frequency will reduce, 0-1 will remain constant. So with this, what will happen is this peak will start coming here and this peak will continue to remain at the same position, nearly the same. Why? Frequency has reduced. Here in single patch, rather nearly square patch, what you will observe, two modes are starting. Observe. Two modes are present. Right? So here with this, what I am doing, I am ensuring two separate resonant modes. With this slot, I am ensuring a proper spacing between the resonant modes, which will ensure these conditions being satisfied, and then it will lead to the optimum CP response. Because see what will happen now, over a range of frequencies, see optimum separation is what? Over the range of frequencies within that band where 0-1 and 1-0 are there, you do get a orthogonal field excitation. See here, optimum separation is something very important. Ultimately, you should have Jx component and Jy component. Their radiation will lead to Ex and Ey fields. Now in the free space over a band of frequencies, I should be having nearly this condition satisfied as well as this condition. Now that will be optimized when you do the optimum separation between two resonant modes. Because see what will happen, if you take them farther away, then at no point over the frequency Ex and Ey will be equal, nearly equal. At no point over the range of frequencies these conditions will be satisfied. So within certain range, when you have an optimum separation, these conditions will be satisfied and then it will give me a CP response. Okay, so here when the optimum separation is satisfied over this say range of frequencies, I ensure that CP conditions, radiations are satisfied, and that gives me axial ratio, because then you plot the axial ratio, you will see axial ratio is going down to 0 dB. So you have a CP radiation. See this point is frequency separation optimum is something very important to understand. That separation optimum leads to proper distribution of Jx and Jy in terms of amplitude, which will effectively give me Ex and Ey, as well as that separation also ensures conditions for phase to be satisfied within pi/2 radius. Okay, so this condition will give me a CP response using a single feed and a simple slot cut patch. Now other variation of this, what you do is, I have taken a vertical slot. Now I will take horizontal slot. What will it will do? Okay, what it will do? It will, here I have taken the horizontal slot. So what it will do? It will reduce TM01 mode, whereas TM10 remains constant. Ultimately the outcome is the same. In first case, you are tuning or tuning 10 with respect to 01. In the second case, you are tuning now this with respect to this, so it will reduce in its frequency. Ultimate outcome is the same. Optimum separations give me CP response. Okay, so these are all single feed slot cut designs for circular polarized response using nearly square or square microstrip antenna. Okay, similar variations now we will talk about in the next lecture for circular microstrip antenna as well as equilateral triangular microstrip antenna. So those configurations now we will discuss in the next lecture for circular polarized antenna design. Thank you.